Hi, everyone. I hope you had a wonderful spring break and got a little chance to get away from your screens and thinking about school. Well, this kind of marks a milestone. This is, I believe, the very last lecture for AP Physics 1. Woo! We're done! And we'll start reviewing soon. Just give you a quick outline of this. Review is Wednesday. We'll go over a few things with a probable test on Friday. After that, the rest of our time is pure review. Yes, let me get the worst news out of the way right away. Your AP exam is scheduled for 4 a.m. in the morning online. It is horrible. We'll talk more about this later. We're gonna have to shift your sleep schedules. If you're in the U.S., great. That's 4 p.m. in the afternoon Eastern Standard Time. But everybody else, it's miserable. We'll talk more about that later. Anyway, we get into household circuits today, and that's what we wrap up our chapter with. Just a quick note on these. As you can sort of see, you've got, whoops, sorry, I almost forgot the other things here. Pretty simple circuits. Live wire means the high voltage, or sometimes it's called the hot wire. This is the one that for most homes that's at 220 volts, unless you're in the US or South Korea or Japan where it's 120 volts. And then the neutral wire is at 0 volts. You can almost think about them connected to like a power source or an EMF source over here, except that, of course, that it's alternating current. There's a main fuse, there's an electrical meter, and then there's a main switch and or fuse box. And then all of the appliances in your home are actually in parallel. So all of these points up here are at 220 volts, and all the points down here are at 0 volts. And so you can sort of see here, it's pretty simple. As you add more appliances in parallel, the total current drawn gets larger. Sorry, I have my patio door open. But the voltage across each appliance does not change. In addition to those two main wires that are dark in black here, there's usually a third connection on most plugs, and that is called the earth wire, and it literally connects to the earth, which you remember the symbol we usually use for that is like this, which we always assume has not charged, so that's also at 0 volts. And you might say, well, wait a second, why do we need a 0 volt input and the 0 volt earth? The 0 volt earth is not necessary, but it provides a wonderful safety, and I'll explain why. So quick question on this one. As more appliances are added to the circuit, what happens to the total resistance? Well, if you add another appliance across here in parallel, remember that the total resistance is equal to the sum of the reciprocals of each of the resistances, R1, R2, and R3. So as you add more terms over here, sorry, it's hard for me to draw. If I add more terms over here, it makes this side larger, which means this must get smaller so that this whole side gets larger as well. So the total resistance is going to decrease. What happens is going to go to the current? Well, if you remember Ohm's law, current is equal to voltage over resistance. Sorry, my trackpad was lagging, so my eye looks really creative. As the resistance goes down, the total current goes up, assuming that the voltage remains constant. And the voltage across each appliance stays constant. It's going to be that 220 volts the entire time. Again, remember, just a quick reminder, kilowatt hours is actually a unit of energy, and this is what you get billed for each month. Fuses and circuit breakers. Every single circuit in your house is protected by a circuit breaker. What do? They limit the amount of current in the circuit. So if you can imagine the 220 volts coming in, it goes through the circuit breaker first, and then it goes to the plug or plugs that are connected in your house. What's the circuit breaker do? It makes sure that the current stays less than or equal to some maximum value. If you look at your house, probably most of each of the breakers that you see inside your fuse box, and you can find them inside your house or apartment, are usually rated for 15 or 20 amps. What happens if a current tries to go through the circuit breaker larger than that amount of current? it automatically shuts off. And you might say, well, wait, why do I want to limit the amount of current? Well, the wiring inside your walls does have a limit. And if you exceed that limit, they get very hot and can actually start fires. Same thing with appliances. If there's something wrong with your appliance and they draw too much current, they can literally burst into flames. The circuit breaker's plan here is to actually break the circuit if the current ever exceeds whatever value it's rated for. And these kind of circuit breakers, the little switch simply pops down and you can reset it. In the old-fashioned fuses, they had a little tiny piece of metal across the middle of this, and it would literally melt if the current got too large. And then you'd literally have to unscrew this the fuse and put in a new fuse. With circuit breakers, you can just reset them. Over here, by the way, are the main circuit breakers. This controls your entire house or apartment. And then these are actually for individual rooms or circuits in your apartment or house. Quick example here. Let's assume that you've got a circuit breaker that's limited to 15 amps. How many 7-watt LED bulbs, which are kind of the standard ones now that people use in their homes, can you plug into or have operating in that circuit before it trips the circuit breaker? Now down here I used a 120 volt circuit and 60 watt circuits, but you get the same idea. As you connect more bulbs, I'm just going to draw the bulb this way, you end up increasing the current that flows out. And my question is, how many can you plug in? So solving this one, just real quick, first of all, how much power can you draw through this circuit? Well, remember, power can be current times voltage, or voltage squared over resistance, or current squared times resistance. In this case, current is 15 amps, the voltage is 220 volts. That's 3,300 watts of power. So now how many bulbs can we actually run? Well, it's a pretty simple calculation then. Each bulb uses 7 watts, so the total power divided by how much power each bulb takes, and you'll discover you can run 471 bulbs on one of your household circuits. That's a lot of light. In reality, for a couple of you might realize, wait a second, it's 471.4 bulbs. Well, you can't run a 4/10 of a bulb, so we round down to this to the smallest integer value, so 471 bulbs. If you tried adding one more bulb, it wouldn't just half light up, it would literally trip the circuit breaker, shut it off. Now, the question about what's going on here. So you've got this plug over here, it's a little smaller on US and Korean plugs. That's the hot one, that's actually at 220 volts. Over here there's a neutral one, it's a little bit wider, that's one that's at 0 volts. But then you also have this additional ground connection that's literally connected to the earth. Well, if you ever look at a plug, you'll see that, and I'm kind of trying to draw this a little bit, it's a little awkward here. You'll discover that the lead or the plug that goes into, here's your cord coming off of this thing, the little plug piece here that goes into the ground is longer than the rest. And you might say, well, why does that happen? So it actually makes connection with the earth before you connect to the power ones. Now, why would you want to do that? Well, let's say inside your drill, and it has a metal body here, it has a connection directly to 220 volts, but the lead that's supposed to go back down the cord, so going back out to the drill and back here, the one that went back to the 0 volts is broken. So now this entire drill and the body's at a potential of 220 volts. If it can't go back to the 0 volt side of the plug, because that wire is broken, what's going to happen? It's going to find another path from high potential to low potential. What's that going to do? It's going to flow down the person through their heart and then down to their feet to the ground, which is, remember, always at 0 volts. What's going to happen? It's going to shock them. So more advanced appliances will actually, if they've got a metal case on them, like a drill or a washing machine or a dryer, will actually connect the metal piece or the metal outside of the drill with a separate wire that goes to the ground. Why? Now what would happen if there was a broken connection inside of the drill and the outside of the drill body connected to 220 volts. Well, now it has a much better conductor back through the ground wire, back down through this point right here to the earth ground. And that most of the current will flow that way, and very little, if any, will flow through the person who's holding it. And this just provides a really, really nice safety path. So you really want to keep that ground if you can, and try not to avoid it. Not all plugs have 3 prongs on them, with the third prong being ground, but most do. In China, it's that bottom connector here, which is actually connected to ground. And again, if you look at your plugs that look like this one's longer than the other 2. Now, what happens if your appliance doesn't, or your plug only has 2 prongs on it, doesn't have a ground? You just have to be a little bit more careful. For example, your Mac charger only has 2, which is why every so often as you run your finger across the aluminum case of your Mac, you can feel a little vibration. That is a little bit potential running down for your feet, back down to ground. It's not ideal, but it's okay. More modern circuits actually add one more feature besides a fuse and the ground connector. They actually have something called ground fault circuit interrupters, GFCIs. And you'll see these very frequently in restrooms or bathrooms where you've got water. In more modern homes, you'll see them at airports. What's going on here? Well, in a normal circuit, what happens? You've got something connected. I'll draw a light bulb here connected to it. And you've got one side at 220 volts and the other side at 0 volts. And the current that flows down this path should be exactly equal to the current that comes back along this path. But what happens if, for example, somehow there's a little piece of metal wire exposed here and a person touches it? Well, now what happens? Well, part of the current now goes down through the person to the ground, because now we've added another path. What happens now? This return current over here is less than the current that was up here on top, because part of it's going down this way. And that's exactly what a ground fault interrupter looks at. It compares the current going through this way with the current going through this way. And if they ever don't match within a reasonable amount of value, it immediately shuts off the circuit. Why? Because it assumes that there's another path for the current. All of the plugs in the school building at Concordia have ground fault interrupters. So automatically, if you ever, for example, came in contact with one of the plug sockets by accident, as you're plugging your Mac charger, it would automatically trip the breaker and prevent you from getting shocked. Well, it would for a brief instant, in the millisecond that it takes to determine, oh wait, the 2 currents don't match anymore. These are wonderful safety features, and they, as long as they're working, prevent any kind of accidental shock through people, which is nice. Ooh, a brain break, which means we're just about the end of notes. This is really short today. Fill in the blanks below to make common words, formate common words, like that. The letters you put in the blanks will spell out shorter words that have something in common. Note number 5 could have several answers, but only one shorter word fits the theme. All right. I can kind of get the first one. The only thing that fits for me I can think of, let me see if this works. Shrubbery? Is that with 2 B's? I think it is. And the letters inside spell R-U-B-Y, ruby. I think I know what the theme is. I'll give you, just take a brief moment, get yourself warmed up again, see if you can figure out the other 4. I'll show the answers in 5, 4, 3, 2, 1, 0. Preternatural. Wow. Sort of like supernatural. Gastroenterologist. Oh, good gracious. Shopaholic. Diamondback. I couldn't figure that one out. Which then all of these, the theme are gemstones. Preternatural. Huh. Anyway, fun words. Oh, yeah, okay, good. So we're just down the last two slides. A lot of you, when you were working on this question with your groups, couldn't figure out how in the world to solve this thing. Let me just quick talk you through it. I lost my pen. How do I normally solve this? I always start from the battery, so I'll draw the battery, and then figure out what's connected directly to it. In this case, I'm going to do the top two first. I can see that the positive terminal of this battery goes to this 2 ohm resistor, which connects to this 1 ohm resistor, which connects back to the battery. So if I draw that, I get something like this. And by the way, I made these 2 ohm resistors right away. But here's resistor 2, here's resistor 1. So resistor 2, resistor 1, connect to the battery, which I made 12 volts because they're going to ask that in this first question down here. Again, remember I'm using my software I use to draw resistors, draws them like this instead of the sort of US way of drawing them, which is a little squiggly line like this. And now as you work around this the other direction, let me start again at the positive terminal, and notice here I can go through this resistor here, resistor number 5, which connects to here, which then connects directly to number 4, back to the negative. So down here I can draw that like this. So here's resistor 5, and here's resistor 4, connected from the positive terminal of the battery directly to down here. And notice I left a little terminal here because you're right, that middle point here connects to some other resistors. And now the next step. From the positive terminal of the battery yet, I go for resistor 6, which connects directly to resistor 8, which connects to that point again, this point down here. How can I draw that? I can draw it just like this. So here's resistor 6, here's resistor 8. They connect in series, and then they connect back to that point. And now from that same point, I can go through resistor 7 and then resistor 3 back to the negative terminal of the battery. So I can draw that like this. And there it is. That's redrawing this circuit in a way that's much easier to understand. And now you can actually figure out the total resistance of this thing. And you might say, whoa, wait a second. Well, think about it for a brief moment. These two resistors are in series. So remember, you just add them. So that's 4 ohms. And then these two are in parallel with this 2 ohm resistor. So what's these two, or all these together? Well, you end up with 1 over R equals 1 over 2 plus 1 over 4. Common denominator would be 4, so I get 2/4. And so R is 4/3. Ew, not exactly my favorite. But okay. And you'll discover the exact same thing for down here. This total resistance, since it's exactly the same, is also going to be 4/3. So what's the total resistance then of this whole side? Well, this whole side of this thing, whoa, is going to be the sum of those two. So the total resistance of this is going to be 8/3 of an ohm. Just 4/3 plus 4/3. And then that is in parallel with this resistance over on this side, which of course is just 2 ohms with another 2 ohm series. This is 4 ohms. And from there you can figure out the total resistance of the circuit. You've got this resistance in parallel with this. And once you've got that, you can easily answer this question up here, because then you can figure out the current flowing out of the battery, which is just going to be equal to the voltage 12 over the total resistance of the circuit. And then B, predict what would happen to the current in resistor 4 if a bulb were added in parallel with it. So I got to find resistor 4. Okay, right here. If you added a bulb in parallel with that, what would happen to the current there? And then I'd like you to talk about it a bit. It's a pretty good question. And then finally, this homework question a lot of people ask about. It's actually a Kirchhoff problem, but I want to just quickly run through it. It's actually in tonight's homework, so people must have been working ahead. The question is then, determine the current in the starter and the dead battery. So maybe I should quick explain what's happening here. If you ever have a car that has a dead battery, and I don't know how to draw this. Here's the hood of one car. So there's a battery inside here. And what you can do is if you ever have a car that has a dead battery, you can pull up another car nearby and connect its battery, positive terminal to positive terminal, with a set of jumper cables. So you can use the power from the one battery to help start the other battery. Sorry, I'm not drawing the entire car here, but you get the idea, hopefully. And this is what's happening here. Here's the good battery with some internal resistance. Here's the dead battery with a larger internal resistance. And in this car with a dead battery, there's a starter, which is just a little electric motor used to rotate the engine to get it running. And so once you have the jumper cables in place, this person in the car with the dead battery is going to try starting their car to see if they can get it running. All right, so enough explanation. Let me quick explain what is happening here. First of all, for Kirchhoff, remember you guess the direction of the current. I'm going to guess that the direction of the current over here, I1, is going upward here. And I'm going to guess that the current here, I2, is going upward here. Now, if you look at this junction, both these currents flow into it. So what's the current going to be going through the starter? It's going to be the sum of those two going downward. Writing the two loops, I'm arbitrarily going to choose these two loops in these two directions. For loop number one, then, we get this. Working around it this way, first of all, I'm going backwards through this resistor, so negative the resistance times the current. I do go forward through this resistor, so it's just 1 times I2. And then over here, batteries, I'm going backwards through this battery and forward through this battery. So going backwards for the 12-volt battery, I write negative 12 over here. And then for going forward for the 10-volt battery, 10 volts, so positive 10 volts here. For this side of the circuit, working on loop number 2, simplifying this down just a little bit gives me this. Negative 12 plus 10 gives me negative 2. For loop number 2, I'm going, I just realized I did this one wrong. I'm going backwards through this resistor, so that should be a negative sign right here. And also going backwards through this one. Oh, no. Yuck, I really chose the wrong direction. And going backwards through the battery. Oh, okay, it works out all right. All of those are negative, which means I can multiply through by negative 1. Wow. I don't know why I did that one. Making it all positive, it just becomes that. Sorry, that's my pet cat saying you're not paying attention to me. Plugging it into your Inspire real quick and solving it, you'll notice that, oops, I guessed I2 in the wrong direction. What does that mean? Not a big deal at all. It just means when you're solving the question, what's the current in the battery? The current in the battery is actually that current going this direction. So the charged battery, or the live battery, is charging the dead battery. So the current's going that way. And then the current through the starter is just the sum of these two values. It actually ends up being this. And I know I've got too many sig figs, but I wanted to show you the fact that it's actually smaller than I1 because it's actually a little bit less current. All the current comes out of here. Part of it goes in here, and then the remainder goes here. And so it's a little bit smaller. With that, your homework tonight, pretty straightforward. You've got a couple of textbook problems. Make sure if you haven't already finished that group worksheet, that it's there yet. And you've got another worksheet here. I'll post the links, of course, to this video on here in just a moment, which is the only way you could watch this. With that, though, have a great night. Wednesday, we'll just spend a little time reviewing. And after that, we'll get into working on the test, which may or may not be optional. I'm still thinking about it. Have a great night. Talk to you soon. Bye.